Hello, and welcome to another Footnote episode of Energy Reads. My name is Kelly Travers, and I am your host. I'm excited to introduce today's guest, Christoph Reinhart. Christoph is a professor of architecture at MIT, working in the field of sustainable building design and environmental modeling. He leads MIT's Sustainable Design Lab and is the director of the Building Technology Program. He is also the head of several spin-off companies with products used in practice and in education in over 90 countries. We recently shared some of his research in the audio article titled Cutting Urban Carbon Emissions by Retrofitting Buildings. While reading this article, I was surprised to learn that buildings can be responsible for more than half of a city's carbon emissions. New buildings are now typically designed in ways to minimize energy use and carbon emissions, but there are still a lot of older buildings that need to be cleaned up. Christoph and his team are working to help this effort. They have launched a publicly accessible website called ubem.io that provides a series of simulation tools as well as a process for using them to help neighborhoods and cities calculate their current building energy use and resulting carbon emissions. And then from there, what initiatives they can take to reach their carbon reduction goals. Christoph, I've been looking forward to this conversation and learning more about your work. So thank you for joining.
Thank you for having me.
One thing I've been wondering, your bio says that you are a building scientist. What does this mean exactly?
That is a good question, and I get asked that quite a lot. Building science is the study of buildings, as the name suggests, and it has various subdomains. So first of all, how do buildings function? And so that has a lot to do with the physics, like the heat flow going in and out of the buildings being physical manifestations in the world. So how do we actually keep the temperature comfortable in places? Now, there are, of course, other components to building science, like how do people operate buildings? How do they set their thermostat? How do they decide when do they decide to open their windows, turn on the lights? So that moves then from physics into the areas of psychology and sociology. Who is living in this building? What can they afford? Then there's, of course, also the big question, how are buildings designed? So what's the process of putting them together? And that puts us really into architecture. And then even as buildings are maintained, facility management, real estate, and so forth. So generally, building science is a pretty wide field. Most building scientists used to be engineers and physicists. So the focus has really, for a long time, been on the physical manifestation of buildings and understanding how they work. But as a wonderful new trend, our field has become a lot more diverse, both in terms of what people are in the field as well as their interests. And the reason for this is really two drivers. One you already alluded to, the recognition that in the age of climate change, buildings are globally responsible for 40% of carbon emissions. So this is obviously a huge opportunity and problem that we have to deal with. And then the other component is that over the last 50, 60 years, we've all started to spend more and more and more time in buildings, where I think the average people still think is 90%, but during COVID, many of us probably spent more than 90% of our time in a building. So the conditions that we are generating in building and the impacts on our well-being are enormous. So hence this ever-increasing interest in the field.
So it's funny that you mentioned physics a couple of times, because I understand that was your original background. So what sparked your shift to architecture?
Yeah, physics, for the reason that I laid out, that's my initial passion and still my passion, and it's useful to have that in building science. But as I already alluded to, there are so many other aspects important for building technology, and I always want to be and aspire to be at the table where decisions are being made. And when you look at the face of buildings, that's, of course, architecture and the people that work with the general public to make and maintain and renew buildings. So that prompted me towards this shift.
Well, speaking of decisions and, to talk more about the article that we had read recently on the podcast, how important do you think it is for cities to really encourage these building retrofits?
I mean, worldwide, we know that by 2050, our expectation is that the global built area is going to double, which is actually quite astounding if you think how many thousands of years we have spent building the buildings that we currently have, that the projection is that we might have twice as many buildings in just under 30 years. At the same time,
That's wild.
that it's a scary and amazing fact. Means it's good to be in the construction sector because you're not going to run out of work. But of course, it also means that we really have to focus that are already existing. New buildings generally tend to be more efficient because we have more stringent building codes in many parts of the world. So if we really want to focus on the main carbon emitters, it's the existing building stock. And in the case of the US, about 2/3 of the buildings that we currently have, well, they will make up 2/3 of our building stock in 30 years, and about a third, half of our current building stock we are adding to our buildings. So overall, retrofitting buildings are inefficient. Old buildings are inefficient, and they constitute the majority of buildings that will be around by 2050.
So do you think making these retrofits are actually going to make a difference to these carbon reduction goals?
Retrofits are enormously efficient, especially the art is really, and this is where our tool is focusing on, what are the lowest hanging fruits for different types of buildings to reduce carbon. And sometimes these are surprising facts. So one of the things that actually saves us a lot is, for example, if you get more energy efficient appliances, say a better dishwasher or a better washing machine, then these systems use a lot less electricity energy. At the same time, they use a lot less water. You can halve your water consumption, and water nowadays is energy in many parts of the world. So you have this double dip instantly, and of course it pays for itself relatively quickly. So doing retrofits in buildings can be enormously efficient. You can, on average, with off-the-shelf technology, reduce the carbon emission of a city's building stock by 60, 70, 80%.
Wow. So do you feel like there's kind of one sure place where a city can start when considering what retrofits to prioritize? Or is this kind of really city dependent?
That is a good question. I would say I have several answers when we think of how we are approaching cities right now. We have developed this app that takes cities by the hand and allows them to explore various upgrades that they can take for their buildings. Let's say we are focusing on all the old single-family homes. We're doing some insulation. We make the buildings a little tighter. Where does this get you to? And very often, well, nobody has a real sense from that before and how this is going to translate at the city level. We know that certain things in certain climates work very well. But I think one of the advantages of us working in workshops with cities and their sustainability champion to go through these processes is they own the results more. It's one thing if I come and I tell you, you have to do this, 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 and this, and it's going to cost an enormous amount of money. And they might not be that interested in that technology for various reasons. They might not even believe that this is the right thing. Sometimes this is counterintuitive. So I think going through this really as a gamification type, so this process of personal discovery can be very useful. And ultimately, I think it also helps to develop a very good carbon emission reduction plan. So general cities, city mayor, city governments, I mean, any government is very good at coming up with outrageous goals. Anybody heard, okay, London or New York or Boston want to be net zero or near net zero in 2050, then the chances if you are the municipality anywhere, you're going to say, I want to be the same thing. So we're going to tell anybody that's our goal without really having a clear mind. How are you actually going to get there? And I think this leads to the situation that you have right now where the administration in a lot of cities don't really even know what to communicate and what to do. Whereas with these reduction plans, it becomes very concrete. You can basically tell every citizen, if you do this, this, and this to your building, if we are all doing this, then we reach our goal. And in a way that liberates the policymaker, because ultimately it's not them, but it's the owners of the building that do this work. So I think these tools are very useful for building consensus around a common goal.
Well, so you mentioned a moment ago that you created an app for this. That's ubem.io.
Mm-hmm.
So I know part of that analysis that you do on these different retrofit policies, you're using something called an urban building energy model, which is UBEM. Can you tell us how this model works exactly?
So maybe it's worthwhile going a step back. If you are in the business of designing an energy efficient building, then for the long term, we've been relying on something that's called a BEM, a building energy model, which is basically a physics-based model that can be linked to an architectural model of the building, which basically calculates based on physics, engineering-based equations, and on a local climate file, the energy use of this particular building. And then for a long term, what we've done then is that there has been a specialty consultant working in key ambitious project with the architect to run these models and say, if we are designing the building in this way, it's going to be very efficient. Now, these models typically take quite some effort because it's one building, it's one architect. The costs are pretty high. So we couldn't just repeat that process with every building in Boston because it would be too expensive. So this is why we started 10 years ago to develop this urban building energy modeling, which is basically a combination of big data, so GIS data, LiDAR data, anything that we have available in our time, which we can scrape and get for all buildings in the city, the form and what the building is used for, how old it is, and so forth. And that we are combining via in the cloud with our physics-based models. We, of course, have to take certain shortcut simplification, but we figured out ways, especially for these early stage policy decision tools, to create a good enough digital representation. Some people might call this a digital twin of a city, to be able to say, okay, we can reproduce what goes on in the city right now. And once we have that, and it's based on the underlying physics, we can do any upgrade you're interested in. Anything you would want to come up, we could basically say what would happen if we applied that to the city. And this is how these UBEM models function. Now, maybe one thing that is interesting to just show the trajectory. When we first came out of this in 2016, we built the first UBEM model of a large city anywhere, and that was in Boston. And that was, of course, MIT worked with the Boston Redevelopment Authority. That was a really expensive project. It was great that we did it. We explored what could be done. At the same time, similar activities happened in other major cities around the world. But this is not something that a small place would be able to afford, even though, of course, most people live in smaller places that don't have the funding. So this new web app particularly focuses on the idea rather than having like an expert user who has to be a consultant and an energy modeler and a big data person. So something that is barely affordable or trainable. We've kind of broken this up into little pieces. We need a sustainability champion, somebody that cares, which just about any town and municipality has. We need a GIS manager, and that nearly everybody has, especially in the US, because our property taxes are linked to a digital GIS model. So this is usually somebody that's the financial bloodline of most cities. So this person exists as well. And then energy modelers are pretty common. So we really, in this case, go through this 8-step process where we bring these 3 parties together and we can dramatically reduce the cost. That's the idea behind the app.
So this question's a little off the rails, but I'm really curious because I was reading the story out loud. And so the model and your website are spelled UBEM. Why is it pronounced UBEM instead of UBEM? Because UBEM just seems like the obvious choice.
I love it. Well, as you might have gathered from my accent, I'm German, and I made up that term together with Carlos Cerezo, who is Spanish. Maybe for us it was natural to say UBEM, and we called it UBEM. Maybe it's like an U-boat. I don't even know. The first person that asked me that. So blame it on my accent that we called it. And I guess that people never questioned how we called it. Maybe some people in the world say UBEM, and there we go. I don't know. That's a great question. I love it.
Yeah. One of those things where I never would have thought of it, except wanted to get it right for the podcast. And when I was watching videos to try to see you guys talking about it and how you're pronouncing it, I was like, wait, what? I have to like double check on this. So anyway, I had to ask.
I mean, well, all the Americans at the lab, nobody ever questioned it. Maybe, they probably all have somewhat German accents after the time they leave MIT with me.
Well, thank you for being a good sport about my question. So to test the website that your team created, you held a 3-day workshop with policymakers from 8 different cities around the world. What surprised you the most about the results from this workshop?
There were a few surprises. And what was really nice from the get-go, how enthusiastic these cities were to participate. When you look at the list of cities, it's in a way quite remarkable. We had Cairo, Singapore, Dublin, Kiel in Germany, Montreal, like Florianopolis in Brazil, some small places in Middlebury in Vermont. And part of this was by design. We just contacted people that we somewhat knew in different parts of the world. And we wanted a variety of climates and we wanted a variety of sizes because we wanted to demonstrate that this works everywhere. But these are not like long-standing collaborators. So, I mean, I was stunned, actually. We contacted a whole bunch and nearly everybody says yes. So that was a nice surprise before we started because we felt this is really, we hit a nerve there, which was very good, right? So that is something that we know cities want to do it. Yeah, I think another component that was nice for us to see is these 3 roles that I talked about, the sustainability champion, the GIS manager, and the energy modeler. We had kind of made these roles up in a paper before when we laid out the concept. And suddenly we met these people, for example, a group in Sandy Springs in Atlanta, who actually had these titles. And I had never met anybody with this title. So again, it was maybe a happy coincidence, but it really showed us that this mold that we created fits actually to where cities are going. And we had tried a couple of times to find the right angle for this technology. So that was really positive. Another thing, like when I go 3 days later after the workshop was done, I would say one of the key things that only after the fact dawned to us that we had somehow forgotten to talk about domestic hot water. Why is that important? So domestic hot water is the hot water that you use in your buildings when you take a shower and any application where you need hot water. And we know that uses a lot of energy. And actually, if you go back to the 80s, a lot of our effort has really been focused about the solar water systems and so forth. But right now, we are so focused on Energy Star appliances, and that's all good, and on photovoltaic and heat pumps for heating, that we found that once you start modeling the cities and all these things were done, nobody had talked about hot water. So we have this significant remainder that, including us, and I would blame that squarely on us, nobody had ever talked about anymore. And so that was maybe one of these little things that where people knew for a long time it's important, but we just are all choosing to ignore it.
Yeah, I think I started thinking about hot water this past winter when I was thinking my home is on natural gas. And so thinking about the fact that, how much hot water I'm using in my shower or to wash dishes is actually making such an impact.
So a low flow shower head halves the water that you use during your shower. I'm not sure if you have one. $15 or so. It's quite amazing what it does. And it's one of these things like solid state lighting, which most people now have. We should all have these kind of low hanging fruit technology.
Absolutely. That's a great one. I'm definitely putting that one in my back pocket. So you said that there are cities that were from all over the place. How big of an impact did these different locations and their climates have on the results?
Climate is, of course, key. Well, first of all, if you're in a very extreme hot or cold climate, then the technology is completely different that people are using. I mean, if you're in Singapore, it's cooling and dehumidifying air to be comfortable. If you're in Montreal, it's heating the air. And in between, there's a mix of different technologies. So climate is very important. Now, I think what we sometimes overlook or be self-evident, is that culture and local interests are really important as well. And so culture has several levels. It has just how do people traditionally put together a building, and in what building typology do you live? When you live in Middlebury, Vermont, or in Montreal, the chances are maybe you live in a single-family home, or you live in a triple-decker. When you live in Cairo or Singapore, you're more likely to live in like mid to high-rise. And these buildings behave very differently. And then another key cultural component is how people want to live. So in a way that is, especially I noticed, and I share that in Europe and here in the US, in the Northeast, people like to live in old buildings that are renovated. So usually when you say, oh, I live in this building, and people immediately brag about if their building is over 100 years old, and then kind of the assumption is that it's retrofitted. I think in many parts of the world, that is not desirable. People want to live in a new home. And of course, when we want to be in the business of selling retrofit, that's a lot easier here than if you would think, I don't want to live in a retrofitted building. I don't want to live in any old building, let alone something that's like a secondhand show repaired, right? So I think those components is really something that I just starting to understand that. And that, of course, has nothing to do with what we've been traditionally building on. This is really more like really fundamentally rethinking how do we acknowledge these cultural desires and operate with them.
And so I know part of the results you found were that these initiatives that these cities had already decided on, it kind of revealed that they actually weren't going to get them to, that reduction goal that they had in mind. And that you kind of later looked further at what decarbonizing the city's electric grid would do. What sort of impact does that decarbonization make?
So there's a lot of focus right now on using more electricity than fossil fuels. So the idea here is when you use electricity with a heat pump to heat your building, then one day we're going to have all electricity being generated from renewable energies. And then that makes sense because once we have wind farms and solar in sufficient quantity, then our grid would, in principle, one day be so clean that us having switched everything towards electricity works very well. And so now, depending on where you are, different countries have different plans, more or less concrete, how they're going to reach this. In the United States, there's actually a pretty comprehensive plan, and you have pretty good predictions of how much carbon is in a kilowatt hour of electricity right now, and how this is going to change and usually go down over time. So that helps you to decide, is it really a good idea to put in a heat pump? And depending on where you are, in some cases today, you might temporarily use more carbon or generate more carbon by switching to a heat pump if you happen to be in a state that burns a lot of coal to create the electricity. But the long-term goal in all cases is that this is going to disappear. So what we did for these cities, we looked at these plans and basically wanted to see how these two effects work in tandem. So on the one hand, you're reducing carbon emissions from the grid. That's something where the city doesn't have to do anything. This just happens to them, not through them. And then on the other hand, when you update your buildings, then hopefully you pick electrically based technology so that you fully benefit from this decarbonization.
One thing I thought was interesting in the article was that you noted that one of the cities you worked with owned both the utility and the natural gas that it burned, and that this actually affected their retrofit choices. Can you speak a bit about that?
Yeah, absolutely. So a lot of cities, I would say primarily in Europe, but in different parts of the world, own their local utilities. And the way that often works is they might have a power plant, but usually they're purchasing electricity or natural gas in bulk, but they own the distribution system. And generally, that's something very good because the utility makes money by definition. There's a monopoly there, and if people use electricity, they make money. And a lot of these cities then use this revenue to, for example, finance public transportation. But on the other hand, of course, there are situations where when you do this, you invested in certain technologies. And in a way, one of the technologies that are harder to deal with is if you have a district heating system that is fossil fuel powered. So that would mean you have basically a fossil fuel, a huge natural gas boiler where you burn natural gas to create heating and you distribute that to a ton of buildings. That has its limitations in the long run due to what we said earlier, that if you want to electrify your heating, you are stuck to a natural gas boiler. So there was less appetite to say, hey, how about we are exploring getting heat pumps for everybody, because that would undermine the financial model of the utility. Now, interestingly, that actually changed pretty dramatically in the last year. This was a Central European city because of the unprovoked war in Ukraine. There is not enough natural gas anymore. So now it's an interesting heat pump out of availability necessity.
Yeah. And so I know like a key limitation, even beyond, the city level, is that for many different clean energy technologies and policies is just getting that buy-in from consumers. Can you speak a bit about how you took this into account for your research and for ubem.io?
Yeah, the buy-in is absolutely key. And in our first iteration of the tool, and this is what we've been talking about, we focused on the kind of technical potential. If you do certain things, how much can you reduce carbon? But of course, you have to very, very quickly, people are not interested in kilowatt hours. People might be interested in carbon. People are interested in money. So without putting some dollar tax and payback numbers to this analysis, the analysis won't get you very far. So we have been working on models just to estimate costs involved, and this is a complicated moment right now to evaluate, because we are trying to ramp up this retrofitting activity so fast that our labor force is lacking behind. We just don't have enough people that put in these technologies right now in many parts of the US, and I would say in the world. And that, of course, leads to admit to short-term distortions, because the few people that are able to do that are overworked, and that drives up prices. But I think that we can understand how this develops in the long run. So then the final component is where we've been working on through the MIT Energy Initiative with some utility partners here, that we started to work on willingness to pay models. So that's where we ask people, how are you willing to pay $500, $1,000, $5,000, $25,000, $50,000 to upgrade your home? And how much would you expect to save each month? What is the payback time? And we asked this to several thousand people, including knowing how much they care for the environment, self-reported, like general income level, ownership of the building, and so forth. So that has actually greatly helped us to have now this, we call it the deal, no deal model. We at least know when people say, oh, it's too expensive for me. Like you probably have 2/3 of people when you tell them, would you spend $50,000 to upgrade your building? They're just going to say no. That number is just, I'm not interested. So that helps us kind of lay out this complex relationship between how much do people care, how much money do they make, what do they expect, so that we can start fine-tuning incentives better. Right now, there is, to kind of get this retrofitting market rolling in the US, there are a lot of pretty blanket, pretty high incentives. And in a way, this is similar to what we've done to photovoltaics. They were really heavily subsidized at the beginning to get a lot of people to get buy-in. And then we're slowly tuning down the support because we know that technology gets more efficient. That works to a degree. Now the question is how fast can we get lower? There's, of course, also an unintended consequence that when you do that, you tend to get higher income households to do this first. If everybody gets the same money, the person who has more money is more likely to say yes, because for them it's a smaller commitment to certain things. So these questions of equity and how we have to break this down, this is really where our activities are currently at, to just help cities to understand these relationships better.
And I know MIT right now is actually currently retrofitting the Metropolitan Storage Warehouse, which, for those familiar with the MIT campus, is the huge warehouse on the corner of Mass Ave and Vassar Street. It's an iconic Cambridge building. It opened in 1895 as a storage facility, and it's now being renovated to house MIT's School of Architecture and Planning. Have you played any role in this project or your model?
A role in the sense that, of course, as MIT faculty, we all try to be very involved in, and to my role at MIT with several colleagues, we've been involved in the architectural process and trying to give our advice. The UBAM software, or UBAM, no, I'm going to say UBAM. The UBAM software is really for larger scale. So we would use what I mentioned earlier, the BEM, the Building Energy Modeling software, to look at that building specifically. And a lot of this work has happened using these tools for this building. I would say where our larger scale work really came in is thinking about the development of the electric grid. So right now, MIT is very similar to a lot of campuses in the Northeast, is that we are using natural gas with a complicated campus utility plant to create heating, chilled water, and our own electricity. And that has been one of the drivers for decarbonizing the grid generally in New England. And it is also economically a good model, which is why a lot of campuses are doing that. Now we are at this interesting fine moment where, fortunately, we are pushing so much renewable energy that we are soon reaching the point at which actually the electric grid, the public grid in Massachusetts, might be cleaner than our own electricity. And for us at the School of Architecture, that was really, really important. We didn't want to move in a building that is basically dependent on a source that might not per se have an immediate future. So there was a lot of lobbying on our behalf to say, well, we would really like to have an all-electric ready campus building. And that is not necessarily the most economic decision, but it's a future-proof decision. And was actually a fabulous experience that, our facilities on campus, the administration, everybody was really receptive to the arguments that we made and in a way committed to spending more. So what we are doing right now is that might be a little complicated. It's for a physicist a really beautiful thing. So what we are doing, we are basically on our campus, we have two loops. We have one loop with hot water and one with chilled water. And every building just comes in and takes whatever they need, right? And so what we are doing is we're using what is called a water source heat pump in that building. So we are taking the cold water that all buildings share and we make it colder. And that colder, that heat we are using to heat our building. So the Metropolitan Warehouse will be heated by making the chilled water chillier, colder on campus, which is cool as an idea. It's a very efficient idea. It also kind of ties us all as a campus more together, physically speaking. So there are a lot of ideas of basically having these grand loops that start connecting buildings, and buildings take and give from it heat in order to benefit from this. So this is something that we've been fortunate all as a team to get implemented right now in the building. We're really excited about that. And it has direct carbon savings for the buildings. I think it was an extra 15% of the overall carbon were saved to that. And it's also something that I would think that was motivated through this work. I'm thinking our cities. The campus is like a mini city. So that helps us.
So to close, I want to ask a fun question. If you could become an expert in anything, instantly download all the skills and knowledge instantly into your head, even if it's not related to what you're doing now, what would it be?
If I'm selfish, I think the most exciting field, if I wanted to just learn something from completely new right now, it probably would be biochemistry and gene sequencing. I think the COVID pandemic taught us just how incredibly our advances have been in the field, given that the technology for the vaccine was weak, in principle available that we could do this. So I think it's an incredibly exciting field. And my daughter enters into this field right now. And this is one of the topics where I always feel completely ignorant. And so I think it's an exciting new field that I would probably, where I see a lot of innovation coming up next. Otherwise, when I look at something that is kind of related to what I'm doing, maybe I would want to become like an influencer YouTuber, because I think if we want to really get to a lot of people and get them excited about retrofitting, then we need the Mark Rober type skills, I think, to make building science is already a little out of the basement of nobody caring about building science, but we still have to bring it more, make it a part of the public imagination.
I love that answer. Christoph, thank you so much for speaking with me today.
Thank you. That was a lot of fun. Great.
Thank you. And to our listeners, thank you for joining. I am Kelly Travers, and this is Energy Reads.